Hey, this is a presentation I gave a few years ago at a LabVIEW user group meeting. Didn't record it, but I wanted to record it now. So this was made in 2018. It's now 2021. So the material might be a little out of date. Like the pricing might not be accurate, but I think it's still relevant. And I probably would rearrange these slides a little bit if I were to do them again today. But all I can seem to find is the PDF. So this is what we got. So I'm going to talk about the National Instruments USB-845X hardware device. It's made for specialized SPI and I2C communication. I'll get into what that means right now. So as a quick overview, SPI stands for Serial Peripheral Interface. And it's a simple master-slave relationship, often used to control simple devices. You can see here a 8-pin chip or a LCD display. You typically need 4 wires for this setup: a clock, a chip select, data in, and then optional it is data out. And then I2C or I2C stands for inter-integrated circuit. All I'm going to say here is that it's more complicated, but I think it uses fewer wires overall. But everything I'm going to say pretty much applies to that as well. Just understanding that it's a more complicated protocol. So again, for SPI, you've got your 3 required lines: clock in the middle, chip select at the top, and then data at the bottom. So every time your clock ticks up, your device is going to read a data bit if that device's chipset select line is low. So here I'd be sending 8 bits or 1 byte, and the actual data would be shown at the bottom. Different devices might configure on the up or the down cycle, but here shown on the up cycle of the clock, that's when data is read. And then typically when the chip select line at the top, SS, goes high, the entire byte is read into the device all at once. So here's a sequence of multiple bytes being sent sequentially. And I think one thing I'm going to point out here is that even though you might have a clock speed that's consistent, in between every 8 bits or 1 byte, you have this delay from your chip select line toggling while the device is reading the information in, and the master device is toggling that line. That's an important thing to keep in mind, because even though you might have a certain clock speed, you're over a long period of time, you're not going to get that clock speed in your data transfer rate. That was a kind of rookie mistake I ran into, expecting my clock speed to be my data transfer speed. And it sort of is, but there's a lot of reasons why it's not, and I'll get into that in more detail. So first, the big question: do you need specialized hardware to talk to SPI and I2C devices? A simple answer is no, you do not. You can do something called bit banging, where you just send individual bits. Pretty much any National Instruments DAC device with 3 spare DIO lines can drive that 2x16 LCD display that I showed earlier. I strongly recommend checking out Kevin Darrah on YouTube or on his website shown here. Really great videos. He's done SPI and I2C bit banging. I did make a demo of this in LabVIEW, but I didn't show it here. I only know why. But if you do want specialized hardware, NI sells 2 products shown here in 4 different lines. And they have the USB-8451 and the USB-8452. The key differences, look on the right, enclosed or not. So each model can come in a plastic case or not. For the 8452, you save over $100 not getting the plastic case. So if you're an OEM or you're going to embed this in some other device, or you just want to 3D print your own case, definitely I recommend not getting the enclosure. If it's going to sit on your desk all the time for prototyping, then I'd probably splurge and get the enclosure, just so you don't accidentally fry something. And then the other major difference between these two is the clock speeds. So I was looking at an SPI device. The 8451 has a 12 megahertz maximum clock speed. The 8452 has a 50 megahertz maximum clock speed. 4x improvement didn't seem like a lot. The device I was looking to talked to had a maximum clock speed of 20 megahertz. So it didn't seem worth splurging for the higher model number with the bigger price tag just to get an extra 8 megahertz clock speed. I did some rough calculations, and that 12 megahertz seemed fine. So that's what I bought. And question is, should you buy the 8451? And the answer, unsurprisingly again, is no. The 52 is pretty good, but for some reasons I'm going to get into, you just do not want the 8451. There's a few, I would say, undocumented, not even bugs, but just outright failures with it that unless you're replacing an existing 8451, just a direct one-to-one hardware swap, I would go with the 52 every time. So the way you communicate with these devices, there's basically three ways. The NI has a set of drivers called the NI 845X drivers. You can download for free. The basic communication in them is more or less bit banging with style. You've got millisecond delays. You're setting bit values that you want to communicate and letting it run. The next level up is scripting. So here you build these batch commands, and I'll show an example of scripting on the next slide. You build these commands that then you pass out all at once to your device, so it can run this suite of commands at the hardware level. And you're limited to 64 messages, I'm calling them. Probably got a little fast and loose with some of the naming here on my end. And then the last method is streaming. I didn't really touch this. This is only available on the 8452, so another reason to go with that device. And this is more for continuously reading data in from sensors. So if you want to read from a sensor that uses SPI or I2C, streaming is the way to go, and you definitely want the 8452. In my case, I was writing data. So here, I didn't label this super well, but I'll walk you through what it looks like to do some scripting code in these drivers. So this is the initialization setup before the loop. You're doing things like telling it the clock rate that you want to use, telling it if it should idle low or high, if it's a rising or falling edge, and just getting your script set up. Then I go inside a loop for 64 iterations, where my message is going to set the chip select line low, write 2 bytes of data, and then set the chip select line high. And then I put in a wait 0 microseconds. In some cases, I was trying to set this to play around with how the script functioned. So I'm able to loop through this 64 times, building up this script of, in my case, 64 different messages I'm sending to my device, each of which, again, takes 2 bytes, which is just how my device works. And if I tried to do 65, I would get a LabVIEW runtime error that there were too many messages in my script. So that is a software enforced limit at runtime. And then the last thing, you just kind of finalize, or not close, but end the script, and then you pass this reference out. And now I can take this reference and I can run it anytime I want, and it'll replay essentially all of this. When I set this up, I'm not actually talking to the hardware yet. So when you're running these scripts, I kind of alluded to it before, there's different types of delays, right? So if we go back here, even though you're sending 3 bytes, in between each byte, there's a delay. So you might have a 12 megahertz clock, but these extra little delays add up to a few tick cycles. So that might slow you down by 20%. So I've identified 4 different types of delay. The first one is that intra byte. So each byte that's being sent is a separate command. And in my cases, I'm sending multiple bytes per message. So that there's a delay in there. So then to complete a message, you toggle your chip select line low or high, and that tells the device to read all the bytes that have been sent and process it. And that time to toggle your chip select line has a delay. And again, there's just no way around that. Let's skip over batch delay for a second. So then script delay, if you're using LabVIEW and using this driver, every time you run this script, all these messages will go as fast as possible, and they're going to be hardware timed. But if you want to run 2 scripts back to back, you're going to be coming back to LabVIEW. And so if you're running LabVIEW on Windows 7 or just not a real-time machine, you're going to have software level delay of like a millisecond, and I really can't get around that. And that's just to be expected. And then last, this is the main reason why you should not get the 8451, what I'm calling batch delay. It's undocumented and incredibly annoying. So I'll get to that in a few slides. I'm just going to run through a kind of demo of all these delays. So here, these are both screenshots of an oscilloscope from the 8451. On the left, we have a 500 kilohertz clock sending 6 bytes of data. Each of these thick rectangles is 8 bits being sent. So that's 6 bytes. And on the right, I've got 8 bytes being sent. They're much thinner lines because we're now running a 24 times faster clock at 12 megahertz. But you'll notice on the left, and the timescales are the same, 25 microseconds per division. So on the left, 6 bytes takes 1, 2, 3, 4, 5, 6, 7, 8 divisions. On the right, 6 bytes takes 1, 2, 3, 4 divisions. So 50% faster, but 24 times the clock speed. So you can see how much of an impact the delay between bytes and the delay between messages takes. It's a huge impact, and another reason why you would think you don't need to go up to those faster clock speeds, because you don't save a lot, and you can save money, but the 8451 will bite you. And I think I'm going to skip over this one. It really doesn't show anything else that the previous slide didn't already iterate. It's just showing the 52 on the left going at the 20 megahertz clock speed. So I'm going to skip that one slide, jump to here. This is what you'd expect to see when you run a script, and this is what you do see on the 8452. I'm just going to focus on this blue section up top, and essentially this is zoomed out to a really long time scale, relatively, and this is 64 messages being sent to my device. So lots of data being sent really quickly, and you can kind of see your time average here. When you run this same script on an 8451, instead what you see is this. So this is what I'm calling batching. You have, I think it's 13 or 14 messages, and then a giant delay. You can see my time scale is 1 millisecond per division. So here in between batches, we have an over a millisecond delay consistently. So what should have taken, I don't know, 1, 2, 3, 4, 5, 6, like less than 2 milliseconds easily, is now taking 8, 9 milliseconds to do. And it seems like these delays are the hardware only has a certain amount of buffer, is my guess, and it needs to flush the buffer after it finishes the 14th message and then refill it. And the really sad thing is, going back to that wait command I put in there, even if you have a really long wait and you run 12 messages, wait, and you want to run 5 more, it's still, when it gets to that 14th message, it'll then empty the buffer, refill the buffer. So it's not doing a rolling buffer. It's not like you're clearing it out faster than it can refill it. It's truly waiting for it to read everything in there, and then it'll refill it. So this delay is fixed. You can see on the bottom here, the device I was trying to talk to is a variable resistor. So here I'm measuring the voltage drop across the resistor. So you can see on the diagonal sections, that's where it's changing smoothly, and that corresponds to where data is being sent, and that's what I want to see. But then I have these nice flat sections where nothing's happening. So where I wanted a nice smooth linear our resistance change, I'm now getting a nice stair step instead, which is not what I wanted. This is not documented anywhere in the device documents or specifications, and I didn't really seem to know about it, and it really bit me pretty hard. So this is why I say do not buy the 8451 from National Instruments, but if you want this kind of device, the 8452 is pretty good. Just again, be aware you have this 64 message limit. It might be different if you're running fewer or more bytes per message. I didn't stress test it that carefully, but And then here's an example of running 2 scripts back to back. So again, I said earlier that 1 millisecond delay between scripts because you're going back to your computer to resend. Potentially this could be done faster, but the setup I was running, this is just how it was. So, and the last point I just want to make, unfortunately, you cannot simulate an 8451 or 8452 in iMacs. I said here they're too lazy to write one. I'm assuming, honestly, that there's just no market and that these devices are not sold very commonly. It is really frustrating, though. You know, we bought one, integrated with the system, and just wanted to send it off to the client, the end user, and have them use it. But that meant that I couldn't run my code without diving in and wrapping all of my 8450X drivers in logic to simulate my own device or ignore the errors. At the end of the day, these devices are just DIO. They're not any fancier. One rep I talked to argued that they were fancier devices simulating, fancier hardware communication protocols, but it's just DIO. There's no reason they couldn't simulate this if they wanted to. As of 3 years ago, they just had not done it. So in summary, you do not need specialized hardware to run this device or these types of devices. If you do want specialized hardware, the NI USB-845X is a pretty good one from National Instruments. There might be others. I didn't look at the third-party market. And if speed or performance is a factor, just be aware. Might be old news to everybody else, but when I was doing this for the first time, your time averaged data rate is much slower than your maximum clock speed. So it's just a trap for young players. But yeah, thank you.